We present Dynamic Tube MPC, an approach leveraging massively parallel simulation to learn tube dynamics for robust safety in the planner tracker paradigm. When solving planning problems in cluttered environments, it is typical to separate the problem into a planning layer, which operates on a reduced order model, and a tracking controller, which takes in the plan and tracks it on the full order system. In this work, we plan on a single integrator model and use a Rabert heuristic to track the plan on the 3D hopping robot Archer. Inevitable tracking error necessitates robustification of the nominal plan to ensure safety. Tube MPC approaches to this problem can be overly conservative and miss the fact that tracking performance depends on the signal being tracked. Here, we see a tube MPC for which the given problem is infeasible as the tube cannot fit between the obstacles. If the input available to our planning model is significantly reduced, the problem becomes feasible, but is quite conservative. Our Dynamic Tube MPC allows the tube size to vary as a function of the planning model trajectory, allowing an agile solution to this problem. Critically, when in between obstacles, we see the planner slowing down to reduce tracking error while moving quickly when away from the obstacles. To train the tube dynamics, we collect a large dataset of planning tracking data using parallel simulation in ICRA. From this data, we learn a tube dynamics model which predicts a tube containing future tracking error from a tracking error history in the planning model trajectory. The learned tube dynamics model is then optimized through in a Dynamic Tube MPC to find a trajectory of the planning model for which the dynamic tube lies in the free space. This allows the hopper to navigate cluttered environments using real-time planning. We deploy this method on hardware. The Dynamic Tube MPC, phrased as a nonlinear program, is solved online using L4 Casati with the SNOPT plugin. By limiting iterations of the solver, we solve the problem at a rate of 10 Hz. Again, we see the optimizer choosing more conservative plans, reducing tracking error when close to obstacles, while choosing aggressive actions with larger tubes while away from the obstacles. This balance between performance and safety is the primary goal of our approach and a critical benefit over other robust planning methods.